Okay, section 4.3, we're talking about logarithmic functions. Before we start talking about what a logarithm is and what it does and why do we care, first of all, I just want to make sure that we can understand that the exponential form and the logarithmic form of an equation tell us the same three pieces of information. They give us a base, a power or exponent, and then they give us the number. I'm just going to call it the number for right now. We're used to this exponential notation where we say 5 to the third power equals 125. In that equation, 5 is the base, 3 is the exponent or power, and 125 is the number that you get when you raise 5 to that third power, which tells you to multiply 5 by itself 3 times. We're used to that notation. The logarithmic form gives you that same information, the 5, the 3, and the 125, but it puts them in different places. So log base 5 of 125 is equal to 3. 5 is the base. It goes by the word log. It's little, it's lower. 125 is the number, and the power, the exponent, is the 3. It goes on the right side of the equation because a log is an exponent. So I just want you to understand these are just two ways of expressing the same information. All right, so we talked about the exponential function, f of x equals b to the x. Now we are going to talk about its inverse function, the logarithmic function. Remember, inverse functions swap their domains and ranges. So if we wanted to try to find the inverse function of f of x equals b to the x, the exponential function, we would change the f of x to a y. We'd say y equals b to the x. We would swap the x and y, change it to x equals b to the y. And then to get f inverse, we would solve for y in that equation. But right now, we don't really have a way to solve this kind of equation for y. Y is in the exponent. How do we get it out? We don't really have a way. So that is what logs are going to help us do, is solve that kind of equation when you have your unknown in the exponent. So the definition of a logarithmic function: if x and b are positive real numbers such that b is not 1, then y equals log base b of x is called the logarithmic function base b, where y equals log base b of x is equivalent to b to the y equals x. So the expression log base b of x means the exponent means log means exponent. So log base b of x means the exponent you put on b, the base, to get x, the number. So terminology, again, in logarithmic form, we call that little number the base. We call the number here, I can call it the number, the argument of the log function. Later, we're going to learn that it's called the antilog. And then this number on the right side of the equation is the exponent. It is the logarithm because log means exponent. I can't say that enough. So when you see this notation right here, what it is telling you is 3 is the exponent you would put on 5 to get 125. All right, so now we can show that the logarithmic function is the inverse function of the exponential function. So the exponential function, remember, is f of x equals b to the x. And if we were to find the inverse of that, we would make it y equals b to the x. And then we'd swap the x and y, x equals b to the y. And then we would try to solve for y. We would have to do that by changing this exponential form to the logarithmic form. Log base b of x equals y. And so that tells me that f inverse of x is log base b of x. So this is the inverse function of the exponential function, and we'll get a better understanding of what we mean by that. Okay, I just want to jump back real quick and talk about this little statement that is in the definition for a logarithmic function, where it says b is not 1. The reason b can't be 1 is because the logarithmic function is supposed to be the inverse function of f of x equals b to the x, the exponential function. If b is 1 in that function, then you're going to have f of x equals 1 to the x power. Now that function is not 1 to 1. Anything you put in for x, you can put in whatever you want. You're always going to get 1. So it is not 1 to 1. Every single x that you put in there gets the value of 1, which means that the domain for the inverse of that function would be only 1. You would only ever be able to put 1 in there because the domain and range would have swapped. That's important. B could never be 1, and that's why. That's why that's part of the definition. So first of all, let's practice changing logarithmic form to exponential form and vice versa. So log base 2 of 16 equals 4. Remember how we rearrange this? 2 is the base, 4 is the log or exponent, and 16 is the number you get when you raise that base to that exponent. Right here, part B, you've got log base B of 1 over 100 is equal to negative 2. Exponential form for that, the base is 10, the power is negative 2, and the number is 1 over 100. Part C, the base is 7, the power is 0, and the number we get is 1. Example 2, now we're going to change these exponentials to logarithmic form. So log, put the word log, and then the base is 3. That's the big number right here. The number we're trying to get is 81, and the power, or the log, is 4. Here, log base 10, and we're going to learn a little more about logs base 10 in a minute. Log base 10 of 1 million. 1 million is the number that is going to be 6. The exponent you would put on 10 to get a million is 6. Now we have 1/5 to the negative 1 power is equal to 5. We would write log, the base is 1/5. The number we're trying to get is 5. The exponent we would put on 1/5 to get 5 is negative 1. So you're just moving those three numbers around in this notation. This is something that you will get more used to. Okay, the equivalence property of exponential expressions says that if b, x, and y are real numbers with b greater than 0 and b not 1, then b to the x equals b to the y implies that x equals y. What that means is that if you have a base raised to a power, and you have that same base raised to a power, and you're saying those two expressions are equal, that means that the powers have to be the same. And so we're going to use some simple logs to kind of talk about what that means. All right, so we've got log base 4 of 16, and that is just the exponent you would put on 4 to get 16. Well, what if you didn't know that was 2? You might say, okay, we'll call it x, and that means 4 to the x is 16. And if you didn't know that was 2, you could say, well, if I write both sides with the same base, then I'll know x is whatever the exponent on the other side is, because if I write this as 4 to the x, and then I write 16 as 4 squared, which I know it is, then I can see that I have the same base on both sides, which means the exponents must be the same according to this property that we just talked about. If I have log base 2 of 8, and I don't know what that is, I'll call it x, I would say 2, the base, raised to the power, x, is equal to the number 8. And I know I can say, I can change 8 to 2 to the third power, so I'll have the same base on both sides. And since the bases are the same, the exponents have to be the same. So you've got log base 1/2 of 8, and you want to know what is that? Well, if you call it x, then 1/2 raised to the x power is 8. That's what that means. And so if I can write both sides with the same base, I'll know the exponents are the same. So I don't like having this 1/2 where the 2 is in the denominator. I know I can write 8 as a power of 2. I'd like to write the left side as a power of 2 also. And I know that if I change the sign on the exponent, it will flip the base. So 1/2, the reciprocal of 1/2 is 2. And so 2 to the negative x is another way I can write 1/2 to the x. And that is going to equal 8, which I know is 2 cubed. And that means that negative x must equal 3 because the same base on both sides means the exponents have to be equal, and so x is negative 3. We're going to talk about logarithms with base 10. These are called common logs because they are very common. We often want to know what exponent would you put on 10 to get a certain number. So this is a very common type of log, and so your calculator has a button for this, LOG. And whenever you see the word log with no base, you know that the base is understood to be 10, and that's a common log. Logarithms with base E are called natural logs, and that also has a button on your calculator because it's something that is used a lot. And that button is LN, which stands for natural log. The base on that log, it just means log base E. So we can evaluate these expressions. Now we know that when I see log and it doesn't have a base on it, it means base 10. So I'm looking for the power you would put on 10 to get 100,000. And I know that that is 5 because I know that 10 to the 5th power is 100,000. And now you've got log of 0.001. Again, that's a common log, so the base is 10. I'm looking for what exponent would you put on 10 to get 0.001. That's going to be negative 3 because 10 to the negative 3 is equal to 0.001. Because when you put a negative exponent on 10, you'll be moving that decimal place to the left. Natural log of e to the 4th, what does that equal? Well, I'm looking for the exponent you would put on e to get e to the 4th. And that exponent would be 4 because if I'm asking what exponent do I put on e to get e to the 4th, well, that's going to be 4. Natural log of 1 over e, I'm asking what exponent would I put on e to get 1 over e. Well, we just talked about negative exponents. If I put a power of negative 1 on e, it will take the reciprocal of e, which is 1 over e. So the exponent you put on e to get 1 over e is negative 1. All right, you can approximate logs using your calculator, and we just talked about those two buttons that we can use. So any common log or natural log, you can use your calculator to punch those in, and I will let you do that on your calculator, however your calculator does that. Usually, with mine anyway, you hit the number first, then you hit log or natural log to find that. Look at your book and see if you're getting the right answers when you punch those in, and you can let me know in class if you need any help with that. Basic properties of logs. Log base b of 1 is always 0 because it doesn't matter what the base is. The only way to get a value of 1 by putting an exponent on the base is to make that exponent 0. b to the 0 is 1. Anything to the 0 is 1. Log base b of b is always going to be 1 because when you're asking what exponent would I put on b to get b, and that would be 1. b to the 1 is b. Number 3, log base b of b to the x is equal to x because what exponent would you put on b to get b to the x? And that would be x. b to the x is b to the x. Number 4, this one's a little tricky. It's a little tricky to understand. I don't think our language has a really good way of saying this that actually feels like it makes sense. But you've got b raised to log base b of x. Log base b of x is the power you would put on b to get x. Well, you're putting that power on b, so you get x. It's a little tricky. So if you have something like 7 raised to the log base 7 of x, that's going to equal x because log base 7 of x is the power you put on 7 to get x, and you just put it on 7, so you get x. Since the logarithmic function is the inverse of the exponential function, their graphs are reflections of one another across the line y equals x because their domains and ranges have been swapped. So whatever was x before is now y, whatever was y before is now x, and so it looks like that. So let's graph a couple of these log functions. Y equals log base 2 of x. First of all, remember that with the exponential function, your x-axis is your asymptote, Now, for the log function, your y-axis is going to be your asymptote. This function is going to be approaching that y-axis, because if you write this in exponential form, y equals log base 2 of x, change that to base is 2, power is y, and the number is x, you can kind of get an idea of what's going on here in a way that is more familiar to you. So if I put in the y values now, instead of putting in the x values, because the y is in the exponent here, if I put in 0 for y, now I'm getting 1 for x, because 2 to the 0 is 1. So the 0.10 is on here instead of the 0.01, like it would be if we were talking about the exponential function. And then if I put 1 for y, 2 to the first power is 2. So now the 0.21 is on the graph. And then if I put negative values on here, if I put -1 for y, I'm going to get 1/2 for x. And so that 0.1/2, -1 is going to be on there. And you can see that as y becomes more and more negative, x is approaching 0. So the function is approaching the y-axis. So it looks like this, and that is the mirror image of the exponential function y equals 2 to the x. So this is y equals 2 to the x, and over here on the right side, the red function is y equals log base 2 of x. So that function is increasing. If that base is between 0 and 1, then you're going to end up with a decreasing function. If you think about it, you could rewrite this log as base to the power y equals the number. And if you made a little chart for that, x and y, now if you put in 0 for y, you're still going to get 1 for x. So the 0.10 is still going to be on this graph. If you put in 1 for y, you're going to get 1/4. So if you might put in -1 for y, it will flip that base and you will get +4. And so the 0.4 -1 is on this graph. So this graph is going to be decreasing. It's still going to be approaching the y-axis from the right side, because you can't get a negative number no matter what you put, no matter what exponent you put on 1/4. But if you give y, if you make y 1, for example, you're going to get 1/4 to the 1 power, that's 1/4. And so x will be 1/4, 1/4, 1 will be on this graph. So if you start putting larger and larger values of y on this 1/4, that is going to make x get really close to 0, but it will never actually be 0. It can't be 0. For the exponential function, the domain is just -infinity to infinity. You can put anything on your base b. There's no restriction on what you can put for an exponent, but your range will only be from 0 to infinity. You can only get positive values. So remember that since logarithmic functions are the inverse function for the exponential function, the domain and range are switched. So with the logarithmic function, your domain is 0 to infinity, and with your logarithmic function, your range is now from -infinity to infinity. Remember, for the exponential function, the horizontal asymptote is the x-axis, so y equals 0. For the logarithmic function, you have a vertical asymptote at the line x equals 0, which is the y-axis. For exponential function, your function passes through the point 0, 1, because you're putting 0 on your base as an exponent, which gives you 1. So the point 0, 1 is on your exponential function. But for your logarithmic function, that point is 1, 0. It flips around. For your exponential function, if your base is greater than 1, that's an increasing function. And that's true for the logarithmic function as well. If your base is between 0 and 1, so some kind of fraction like 1/4, like we just saw, you're going to have a decreasing function. And that's also true for the log function. It will be decreasing if the base is between 0 and 1. We can graph more complex logarithmic functions just using our transformations. So here you've got f of x equals log base 2 of x plus 3 minus 2. So you know the basic log base 2 of x function is this black function right here. We just graphed it a minute ago. Here you are adding 3 to your x, which means that you are translating the graph 3 units to the left. So you can see that's happening right here. So that purple graph is just log base 2 of x plus 3. And then here you're subtracting 2. That means you need to translate that function down 2 units. So all these points are going to come down by 2 units for that. So that would be another way that you could see what these graphs are going to look like, would be to just think about the original, just basic log function base 2, and then whatever the equation looks like, you can use translations to figure out what that graph's going to look like. All right, the domain of the log function, your argument has to be positive. Whatever you're taking the log of has to be positive, because if your base is positive, which it always is, then no matter what power you raise it to, you'll never get a negative number. So it would be impossible to have an argument that was negative. So when it says to write the domain of these functions here, it just means what values of x are going to make the argument positive. So 2x plus 4 has to be greater than 0, which means that 2x has to be greater than negative 4. So x has to be greater than negative 2. So the domain for this function has to be from negative 2 to infinity. And we don't include the negative 2 because the argument cannot be 0. It has to be positive. Natural log of 5 minus x. Again, all that matters is that the argument is positive. So 5 minus x has to be greater than 0, which means that negative x is greater than negative 5. And then if you multiply that by negative 1, you have to flip the sign. So x would have to be less than 5. And so we would just write that as negative infinity to 5, and we would not include the 5. This function, common log of x squared minus 9, you have to have x squared minus 9 has to be greater than 0. That's x plus 3 times x minus 3 has to be greater than 0. And notice, you can't just add 9 on both sides and take the square root on both sides. Because what does that mean? X is greater than plus or minus 3. It doesn't exactly make sense. So you can set up a chart. Remember that if these two factors multiply together to give you something positive, which is what greater than 0 means, they're both going to have to be positive or both negative. One can't be positive and the other negative, and vice versa. So if you set up a little chart with the factors, x plus 3, x minus 3, and you think about where the zeros are from negative infinity up to negative 3, that's when the function changes signs, because at negative 3, the function is 0. And then from negative 3 to positive 3, because it changes sign again at positive 3, and then from 3 to infinity. All right, so in the interval from negative infinity to negative 3, this factor right here is negative, because if you put in, say, negative 4, you're going to get a negative value. Same thing with x minus 3. It also is negative on that interval. So therefore, negative times negative is positive. This is a good interval. That interval is in the domain because that's where the argument will be positive. From negative 3 to 3, if you look at a number in that interval, 0, for example, 0 plus 3 is positive, but 0 minus 3 is negative, which means that the factors multiply together to give you a negative. And so that's not okay. You can't have a negative argument. From 3 to infinity, x plus 3 is positive and x minus 3 is positive also. So that means their product is positive, and so that's okay for our domain. So from negative infinity up to negative 3, and that is union 3 to infinity, and that's what we saw in the graph. That is when you will have a positive argument. Okay, we have a word problem here that partly involves logs, but not too deeply. So the intensity I of an earthquake is measured by a seismograph. So intensity is this letter I, a device that measures amplitudes of shock waves. I sub 0 is a minimum reference intensity of a 0 level earthquake against which the intensities of other earthquakes may be compared. So this is just some value that probably some seismologist came up with. The magnitude m of an earthquake of intensity I is given by m equals the log of I over I sub 0. So magnitude. Determine the magnitude of the earthquake that devastated Haiti on January 12, 2010 if the intensity was approximately 10 to the 7.0 times I sub 0. So magnitude is what we're going to do. We're going to plug this into this formula that they gave us. So log of I right here is what they tell us is 10 to the 7.0 times this number I sub 0. And in the formula, the denominator is I sub 0. So I sub 0's cancel, and you just end up with common log of 10 to the 7.0. And we know that the exponent you would put on 10, because this is a common log, remember the base is 10, the exponent you put on 10 to get 10 to the 7 is 7. So that would be the magnitude of that earthquake would be 7.0. For part B, what magnitude was this earthquake in Washington, D.C. in 2011? They're giving us that the intensity of that earthquake was 10 to the 5.8 times I sub 0. And the formula has also I sub 0 in the denominator. And so those cancel, and you end up with the log, which is base 10, of 10 to the 5.8, which again is 5.8. So that was a 5.8 magnitude earthquake. And then in part C, it says how many times more intense was the earthquake that hit Haiti than the earthquake that hit Washington, D.C. The intensity of the first earthquake was 10 to the 7.0 times I sub 0. And the intensity of the Washington, D.C. earthquake was 10 to the 5.8 I sub 0. And so the I sub 0's cancel, and then you're dividing like bases, so you're going to subtract the exponents. And that is 10 to the 1.2 power. And if you punch that into your calculator, it's about 16. So it was 16 times more intense, the Haiti earthquake.